All right, so now we're going to start talking about torque. Torque is the measurement of a turning force, if you will, and that's not a great definition. It's not actually a force, but it kind of is. It's something that causes things to rotate. Now, technically, it's the cross product between the lever arm and the force that you're trying to apply. Now, cross product means get the perpendicular component. So if I have a radius of some lever arm, maybe it's a wrench, maybe it's anything, measured from the pivot point, wherever the object turns around would be your pivot point, and so object rotates around it. The cross product is all about getting the perpendicular component of the force compared to the radius. In other words, notice here my force is at some angle, and so I'm actually going to end up looking for this component. F, what's here, I'll label it F perpendicular to, and the way I have it drawn, it'd be the y-axis, right? But F perpendicular to the radius, because the only part that causes the torque is the component that pushes, if you will, straight down, 90-degree angle compared to the radius. So the cross product actually takes two vectors, a radius vector or a distance vector, displacement vector, and a force vector, and ends up getting the perpendicular component of them. Where they're both perpendicular to each other. So if you just want the magnitude, and this is the equation that we're going to end up using a lot. If you just want the magnitude, you can use torque equals RF sine theta, and you'll see a lot of times I'll end up switching. I'll do FR sine theta many times, just because I don't know, it seems to flow out a little bit easier for me. Units, Newton's meters, Newton's time meters. Notice also work is in Newton meters, and we combine those two to be the joule. Here we're not combining those two because work is all about having a force and a distance that are parallel, and this is having a force and a distance that is perpendicular. So to indicate the difference between the two, we don't combine that into the joule. The joule is a completely separate thing for whenever the two are parallel. These are perpendicular to each other. Equation there. Now, anything can actually have torque, not just if you have a lever arm, you know, a seesaw, maybe it has another side around a pivot point. Diving boards, anything that turns. I'm going to do a diving board problem in the next video. Including wheels, right? You have a radius of a wheel, a force being applied, you angle between the radius and the force where it intersects the outside, because that's how much leverage you have. Bigger wheels give you more leverage, thus more torque. And then an angle between them. Now I have this setup drawn to where my theta is 90 degrees. So wheels also, anything that rotates experiences torque. Last thing that I want to point out with torque is that you actually, the distance and the force, whenever you combine them using the cross product, the torque doesn't go the same direction as the force. The torque actually goes in the other axis. So if your distance is in the x and the force is in the y, the torque goes in the z. More discussion on that later. All right, now for a very simple example problem. I have a wrench, a bolt. The bolt actually requires 350 Newton meters of torque to turn. If you don't apply that much torque, it won't turn. That's the turning force, right, to cause a nut maybe on a bolt or a bolt to turn there. So I get out a wrench, try to turn it. But because of the angle, let's say, maybe the bolt or the wrench, or you know, the bolt is in an odd location, and so wherever you put your wrench in, the best angle you can achieve to actually push on it is 75 degrees. You're going to have to push slightly at an angle. I don't know if it's, maybe we can imagine that it's under something, or that it's on a machine that you have to reach around in, or car, or something odd, where you have only, you're not able to get perpendicular. The best angle you're able to get 75 degrees, and the maximum force that you're allowed, that you can push with, is 320 newtons. How long D must the wrench be? How much distance do I need here? And let's not use D, let's actually use R, because that's the radius that we're talking about there. Yes, it's a distance, and it's always measured from the pivot point. The pivot point here is going to be the spot that it turns around, which is the actual nut. So how long of a wrench do I need to get? Notice also angle, and I didn't mention this in the last slide, I should have. The angle is always measured between the radius and the force being applied. So whatever that angle is, not over here on the other side, whatever the angle is between the radius and the force. Sometimes you'll see angles being measured relative to the perpendicular, so up here. Make sure to do 90 minus to get the angle between the radius and the force. Now this is just a plug-chug problem. So I rewrite my torque equation, and now I just need to substitute in. And with sig figs, I need a 1.1 meter long wrench, which, if you think about it, is actually a rather long wrench that you would need to be able to apply this much torque. The nice part about torque is using the exact same amount of force, if you increase the radius, aka get a longer wrench, then you're going to be able to get more torque out of it. So if you have to apply a lot of torque, and you are limited in the amount of force you can apply, because you're just a human, you can't apply any extra force than you have strength. So if you need to apply more torque to be able to turn something, all you need to do is go get a longer wrench or a longer lever arm. The longer your lever arm, the more torque that you can have.